Welcome everyone! I'm presenting WikiDBs, which is a corpus of relational databases from Wikidata. I'm Liane Vogel and this is joint work with Carsten Binnig. Our motivation is to facilitate data engineering tasks, which currently still require high manual effort. Tasks like data exploration, data transformation or data cleaning need a lot of human involvement and expertise. With the rise of AI, models have been developed to assist with tasks like column type annotation, missing value imputation, or entity matching. However, the first generation of models was trained for a specific task on a specific dataset, which makes generalization to unseen data nearly impossible. Recently, table representation learning has made a lot of progress by learning the characteristics of tabular data. More capable models, for example tabular language models, have been developed, adapting the pre-training and fine-tuning paradigm, where a model is trained on a large amount of data, which allows to transfer the model more easily to unseen tasks and datasets. However, the tabular representation learning community currently focuses only on single tables, such as web tables or CSV files. But most companies also work with databases, where information is saved in multiple connected tables. Let me show you in an example why we believe that multi-table data deserves more attention. Let's look at the task of table name detection. Imagine that we have a single table with the attributes title and year. It is hard to tell what the missing table name is: music albums, movies, or books. But if we now have a second table called actors available, it is much easier to infer that the missing table name is most likely to be movies. Therefore, we believe that for many tasks, neighboring tables and databases can provide important context information. In order to train deep learning models, we need large tabular datasets. Where are we regarding tabular datasets? There are multiple datasets openly available. Often used are, for example, the WDC web table corpus, WikiDBs, or Git tables. However, they contain single tables, like web tables or CSV files. But for research and databases, we need datasets that contain multi-table data. We could only find 3 collections online, which are the Git schemas dataset, the relational dataset repository, and the SQL share corpus. Unfortunately, the Git schema dataset includes just the schemas, but no table content. The other 2 datasets are rather small and include only a small number of databases. We therefore believe that a new database corpus is necessary, that is large enough to train deep learning models, includes database schemas and table contents with content from various domains, and that also includes real-world data and not only generated data. In our work, we introduced a new corpus called WikiDBs, where we extracted 10,000 databases from Wikidata for various domains, for example from literature, finance, biology, and many more. Each database has a set of characteristics, such as the number of tables, number of columns, or number of rows. All these characteristics should reflect the properties of real-world databases. Enterprises unfortunately do not share that statistics, therefore we rely on public resources. For the number of tables per database, for example, a very useful resource is the Git schemas dataset by Till Dümen. It includes a large number of real-world schemas from public Git repositories. I've mentioned before that it includes only the schemas and no table contents, but for inferring the number of tables per database, that is sufficient. Therefore, we've modeled the distribution of WikiDBs analogously to the Git schemas dataset. Here you can see the distribution of tables per database. Around 19% of the databases in Git schemas have 3 tables. So also in WikiDBs, 90% of the tables, that's around 1,900, contain 3 tables. For further characteristics like the number of rows or columns, read our paper or look at our poster to see how we derived them to be close to real-world databases. Next, let me explain how the construction process of a database works. Let's look at a database from the literature domain more closely. Our dataset is based on Wikidata, which is a large open-source knowledge base that contains real-world data. Here you can see the item in Wikidata for the book 1984 by George Orwell. Data in Wikidata is saved in a document-oriented way. So how can we construct a table from it? We used the saved property information like the author or publication date as columns of the table. Now we filled the first row, but how can we construct additional rows? We make use of the instance of property that is saved for many items in Wikidata. For example, the book 1984 is an instance of literary work. This allows us to search Wikidata for other items that are also an instance of literary work. We find further books and add the information to our table. Now we've built a first table. How can we construct a database with multiple tables? Some of the columns include values that are Wikidata items on their own. For example, the author column. So every author has an own Wikidata item, including further information. This allows us to build an author table, which we can connect to our books table with a foreign key relationship. We then fill the new connected table with information for each author, such as the date or place of birth. This is how we constructed 10,000 databases from Wikidata, always starting with a random concept. We performed some initial experiments on our new corpus. The aim of our experiments is to show that considering multi-table data can improve the performance of data engineering tasks, as shown in the example tasks for table name detection in the beginning. Our setup is to compare two different models on 3 data engineering tasks. The first model is RPT, which is a language model designed for single table data. The second model is a relational pre-trained network, which we designed specifically for multi-table data. It is a combination of a language model and a graph neural network. Here you can see our results on the tasks of missing value imputation, column name detection, and table name detection. You can see that for every task, the multi-table approach in the lower line is able to improve the accuracy. This shows that indeed, incorporating context from multi-table data does improve data engineering tasks. If you are interested in using WikiDBs, you can download the corpus on our webpage. In conclusion, WikiDBs enables new representation learning methods for multi-table datasets. For example, foundation models for relational databases, which allow for 0 and few-shot settings on unseen data. Furthermore, the corpus allows unified benchmarking of different approaches for data engineering tasks. In future, we plan to extend WikiDBs with more data, larger table sizes, and other languages. We plan to do a detailed comparison to other datasets. And furthermore, we plan to leverage WikiDBs for new model architectures on multi-table data. This concludes my talk. Feel free to get in contact via email.